Please confirm so that I can continue.
Yes, sir. Tirath sir, your voice is clearly audible and your slides are also visible.
Okay. So what I am talking in the previous lecture is the basics about ABC. So here from this diagram I have explained that how the employed bees exchanges the information that they are having about the food sources, right? The quantity, the quality, and whatever it is, they just share the information with the onlooker bees which are waiting at the beehive, and based on the information they receive, means the onlooker bees receive the information from the employed bees, and based on the information that they receive from the employed bees, they will take the decision that whether we have to explore the same whether we have to exploit the same food source, or we have to go to another food source, right? So based on the information they receive, they will take the decision. So the most important part of the hive with respect to exchanging information is the dancing area, because in the dancing area they will exchange the information, and communication among bees related to the quality of food sources takes place in the dancing area, that I have already said to you. So, and this dance is called waggle dance, and through the waggle dance they just share the information that they are having. So employed foragers share their information with a probability proportional to the profitability of the food source. Means I mean, whatever the information they exchange with the onlooker bee based on the probability which is nothing but the proportional to the profitability of the food source. Means about the food source, if they get profit, so based on that only they just share the information. And the sharing of this information through waggle dancing is longer in duration, because so many bees are there and they are doing the dance, so it takes time to share this information, because with the help of this information they have to decide which food source is to be selected for collecting the food. So the onlooker bees on the dance floors decides to employ herself. Remember that an onlooker on the dance floor decides to employ herself at the most profitable source. Onlooker bees can become a employee bee as well, right? Based on the information they receive. So there is a greater probability of onlookers choosing more profitable sources, since more information is circulated about the more profitable sources, because many of the bees shares their information with the onlooker bees. After getting all the information from many employed bees, they just want to select the food sources that is more profitable. So as I have already told, the artificial bee colony contains three types of bees. One is called scout bees, which helps to abandon the food source and to choose the new food sources, because they will search the food sources nearby the hive, right? And onlooker bees takes the information from the employed bees about the food source, the quality, quantity, and each and everything. And employees bee is responsible to collect the food and to deposit the food into the hive. Ultimately, bees the main job is to maximize the food at the hive. So the ABC generates a randomly distributed initial population, as in the similar fashion as we have generated the random initial population in the CSA also. So in the same way, random solution is generated in the population. So where SN denotes the size of the population. There we have represented NP, the number of population. Here SN denotes the size of the population, means the number of solution. Okay. So each solution xi, where I ranges from 1 to SN, and SN is the population size, and D is a dimensional vector. That is nothing but the dimension to explore the areas. Okay, so the same thing, how many solutions we are having in the population, SN, and D dimension has been taken. So after initialization, the population of the positions is subject to repeated cycle. We can populate, I mean, see, there is the cycle number, and the MCN is nothing but the maximum cycle number. You can treat it as a, I mean, see what it called, means when we have to abandon a particular food source. Okay, so C is equals to 1 to this cycle is updated when we are iterating the iteration. So it will be updated, the counter for the cycle will be increased, and when it reaches the maximum cycle number, that particular food source will be abandoned, okay, of the search processes of the employed bees. And similarly for the onlooker bees and scout bees. So there are basically three phases in the ABC. One is called employed bee phase, the onlooker bee phase, and the scout phase. So we will see one by one. So an employed B produces a modification on the position. As you know that in the initial population we are having the solution, and the solutions are to be updated over the iterations in order to get the better solution. So an employed B produces a modification on the position in her memory depending on the nectar amount, that is the fitness value. The fitness value, because see there is the objective function that needs to be optimized. So based on that they will update the solution. So the employee B produces a modification on the position, that is the updation in the position in her memory depending on the nectar amount, that is the fitness value of the objective functions of the new source. So whenever we will get the new source or the new solution, whether the solution is to be updated or not, it is based on the fitness value. So provided that the nectar amount of the new one is higher than that of the previous one, if it is higher, then only we have to update the solution, otherwise we can keep the previous solution. So the B memorizes the new position and forgets the old one. If the new solution improves the solution, if the new solution is better, then it just forgets the old solution, it just memorizes the new position. After all employed B's completes the search processes, if suppose we are having, I mean 10 B's are there. If 10 B's are there, so 5 B's will act as an employed B and 5 B will act as an onlooker B. Means 5 B is responsible to search the food and collect the food and deposit the food into the hive, and the 5 B's are just watching at the hive in order to take the decision, right? So they share the nectar information of the food source. Who share the nectar information of the food source? Employed B to the onlooker B, and their position information with the onlooker B's on the dancing area. So an onlooker B evaluates the nectar information taken from all employed bees and chooses a food source with a probability related to its nectar amount. As in the case of the employed bee, it produces a modification on the position in its memory and checks the nectar amount of the candidate source. Okay, providing that its nectar amount is higher than that of the previous one, the bee memorizes the new position and forgets the old one. Now, an artificial onlooker B chooses a food source depending on the probability value associated with the food source PI. So how PI is calculated, the probability, because it chooses the food source. Who chooses the food source? Onlooker B chooses the food source based on the probability. And how the probability is calculated? So the probability of I is associated with the solution, right? Probability I is, because we are having I is equals to 1 to Sn. Okay, I is equals to 1 to Sn, and we have to calculate fitness of all the solution, that is fit I. Fit I is nothing but the fitness value. So we have to calculate the fitness of all the position, that means all the employed B's, and based on that, and see here, Pi is equals to fit I divided by summation of all the fitness of the solution that we are having in the population. That is why here n is equals to not n, I is equals to 1 to n. It should be I is equals to 1 to n. Wrongly written here, n is equals to 1. So how, I mean, this probability is associated with all the food sources, or you can say all the bees, employed bees. So based on that, we can calculate the probability, and with the help of this probability only, the onlooker bee chooses a food source, right? Food source in order to get the food from that particular food source to hive. Here fit I is the fitness value of the solution I, and Sn is the number of food sources, which is equal to the number of employed bees. That I have already said. Okay. So in order to produce a candidate food position, from the old one in memory, the ABC uses the following expression. This expression is used by both the bees, employed bees as well as onlooker bees. But onlooker bees chooses, how onlooker bees chooses based on the probability, but how the solution is updated based on this particular equation. So Vij is the new updated solution, that is equals to Xij, that is the old one, plus phi ij. Phi ij is a random number between 0 to 1, is a random number between 0 to 1. Xij is the old solution, and minus Xkj is the partner solution. Okay, suppose we are having the as you can ask, what do you mean by partner solution? Okay, you may ask, what do you mean by the partner solution? So the meaning is that the partner solution is nothing but the, suppose I have given the example that in the population, suppose we are having 10 bees. In the population we are having, suppose we are taking the 10 bees. So in the 10 bees, 5 bees will act as an employed bee and 5 bee will act as an onlooker bee. So what we are doing is the 5 bees is to be updated, the solution with respect to those 5 bees is to be updated. And suppose I am going to update the first solution. So first solution, for that, here you can see instead of I mean, see, I ranges from 1 to Sn. This is the population size. I ranges from 1 to Sn, which is the population size. So first, suppose we are going to update the first solution. So, or J, what is J? J represents the dimension. Here J represents the dimension. So J ranges from 1 to D and K ranges from 1 to Sn, and similarly I ranges from 1 to Sn. Remember that I does not is equals to K here, because we need to choose the partner in order to update. If I am going to update the first solution, so to which with respect to which other solution we are updating this solution. So other than the first solution, we are having 4 more solutions. So here what we are saying is I is representing the row and J is representing the column. Here we are taking I is equals to 1, means we are going to update the first solution, right? I is equals to 1. First we are going to update the first solution, and if you are going to update the first solution, to which dimension we are going to update. So with respect to jth dimension, suppose we are going to update, you can choose anyone from 1 to D, right? Because we are updating the solution, ultimately we have to have the updated solution. But how the solution is updated? Based on which dimension and based on which partner. Partner means to which solution, the other solution. 4 more solutions we are having if we are updating one solution. So if we are taking, suppose K is equals to 3, that means with respect to third solution, we are going to update the first solution. With respect to the third solution, we are going to update the first solution. If we are taking K is equals to 3, and remember that I does not is equals to J, you cannot take 1, means you are going to update the first solution, again you are taking K is equals to 1. This will not happen. That is why it is written that K is determined randomly. It can be anyone other than I. It has to be different from I, and J represents the dimension. To which dimensions we are going to update? Only one dimension is to be updated, because we are going to update the solution. Solution can be updated to a particular dimension with respect to one of the other solution. That is the main meaning of this particular equation, right? Is there any doubt in this particular search equation how the solution is to be updated? Because this search equation, or with the help of this particular equation, the solution is modified, and it has this solution is employed by employed B as well as onlooker B. Okay, so phi ij is a random number between -1 to 1. So this is the equation by which we can update the solution. One more thing is that as you know that for each and every function there is the lower bound and there is the upper bound, right? So if suppose the whatever the value we are getting, that is beyond the limit. I mean, it does not lie between lower bound and upper bound. So what we can do is, if it is not lying between upper bound and lower bound, so what we can do is we can apply this particular position. Xij is equals to xj minimum plus random number 0 to 1 xj max minus xj minimum. That is written. The food source of which the nectar is abandoned by the bees is replaced. The food source of which the nectar is abandoned by the bees is replaced with the new food source by the scouts. This is the main meaning of scout. In ABC, providing that a position cannot be improved further through a predetermined number of cycles, which is called limit, then the food source is assumed to be abandoned. And if the food source is to be abandoned, what we can do is we have to randomly generate that particular solution, because that solution is not improving. Suppose we are having the 5 bees here. Now, in population we are having 5, and in 5, suppose one solution is not improving till the cycles. We have already set the predetermined number of cycles, that is MCN. We have already decided MCN here. Now, MCN. If MCN is reaches, right, and a solution is not improving. If solution is not improving, so what we can do? We have to abandon it. We have to discard it. We have to discard that particular solution from the population. If we are discarding it, we have to generate the new solution, and the solution is generated randomly. And to generate the new solution, what we have to do is we have to utilize this particular equation. So in that case, because in the jth it is not, I mean, that ith solution is not improving in the jth dimension. So what we can do is xij is equals to xj minimum. We can take the xj minimum plus random number between 0 to 1, and we can use xj maximum minus xj minimum. With the help of this equation, we can generate the random solution in that particular for that particular solution, because that particular solution is not improving. And what we are saying that after this particular equation, if whatever the solution, the value of x we are having, if it is not lies between the lower bound and upper bound, so what we can take is, suppose if it is beyond lower bound, so we can take minimum of lower bound, or br, suppose -5 to 5. I'm just taking the example of range of -5 to 5. Suppose it is -6. We are getting -6, means that is beyond lower bound. So we have to take the minimum of -6 and -5. -6 is the value that it is giving, and -5 is the minimum value, that is the lower bound. So we have to keep -5. If it is suppose in the maximum side, suppose 5, and we are getting suppose 10, so we have to take the maximum of 5 or 10, right, for that one. Now, ABC control parameters. As in the CSA, we are having the flight length, we are having awareness probability, we are having in the same case here also we are having many parameters. And what are the parameters of ABC is the swarm size, the employed bees. 50% of swarm act as employed bees. I have already told you, if we are having 10 bees, so 5 bees will act as employed bees and 5 bees will act as onlooker bees. And out of those 10 bees, only one can act as a scout bees. Out of those 10, anyone can act as a scout bees. And there is a limit. There is the limit, that is the cycle number, and there is the dimension, that is D. These are all the ABC control parameters. Now see, consider the optimization problem as this is the optimization problem. Minimize fx is equal to x1 square plus xt square, and here the value of x1, x2 can be between -5 to 5. This is the problem that needs to be minimized. Okay, and how to find out the control parameters? So colony size is nothing but we are taking 6 colony size. Colony size is 6. So if colony size is 6, so in which three bees, colony size is means 6 bees we are taking. Only 6 bees we are taking.
I think we are having some network issue from the speaker side. Let me connect with him. Please stay tuned for the session.
Sorry for interruption as my internet connection has been lost. So again, I have restored it. Just I wanted to know to which slide, up to which slide you have listened. Anyone just confirm up to which slide I have covered? I'm just requesting the participants and other faculty members and the coordinators, just confirm from where I have to again explain. Whether I have explained the search equation, this search equation.
Yes, sir. You can continue from this slide. That
this slide only,
visible to us. Yes.
Okay. So what I am explaining here, it is that like in case of CSA, we are having the updation equation for search space, I mean to update the solution. In the ABC also, this equation is utilized in order to update the solution. So here Vij is nothing but the new solution that we wanted to get, and based on the Xij. So this Xij is the old solution in the population, and phi ij is nothing but the random number in between 0 and -1 and 1. Yes, it is not 0 between 0 and 1. Phi ij is nothing but -1 to 1 in case of ABC, but in case of CSA, there we are having random number that is in between 0 and 1. Here phi ij is between -1 and 1. You can easily implement it by taking the random function between -1 and 1, and here you can see Xij is the old value, and then we are having Xkj. So with the help of Xkj, we are updating the solution of Xij. So we will get Xij new, and Xij, this Xij is nothing but the old value of Xij, where I is nothing but the index for the sample, I mean not sample, for the solution. If I taking I is equals to 1, that is the first solution in the population. If I am taking I is equals to 2, that is the second solution. So suppose I am taking I is equals to 1, I want to update the first solution in the population. Here you need to tell that to which dimension, for which dimension you are going to update it, that is J. If you are taking the J, we have there are D dimension from 1 to D. So for what dimension, which dimension you are going to update the solution. Ultimately you can take any dimension, you can update the towards the first dimension, second dimension, or any dimension. Suppose I am taking J is equals to 2, regarding, I mean dimension 2, we are going to update it. Now here one more thing is there, K. So K means what? K is different from I. Remember that K should be different from I, because we are going to update the solution 1. Suppose I is equals to 1, we are going to update the solution 1 with respect to the dimension J is equals to 2, and with respect to the solution K is solution K. So K should be different from I. That is very important, because we have taken the example of 5 Bs, 5 employed Bs are there. We are going to update the solution of B1. So B1 will be updated along dimension J, and with respect to the some other solution, and some other solution are 4 other solutions are there. You can take any 4 solution, any one of the 4 solutions. So suppose I am taking K is equals to 3, any one you can take from 2 to 3, because we are updating the solution number 1. So K should be different from I. That is why here K is written. It is written that K is determined randomly, and it has to be different from I. So with respect to that only, that particular partner of that particular solution, we can update the first solution. So this is the solution. This is the equation by which we can update the solution into the population while we are having into the next iteration. So the foods. One more thing is that whenever we will get the value of X, right, value of X, we can update any one dimension, because suppose we are having the 2 dimension. So X1 and X2, like here we are having the X1 X2, we have taken, there is the problem X1 and X2. So either we can update X1 or we can update X2, any one dimension. So if suppose we are updating here X1, if X1 is not lying between -5 to 5, so whatever the value that we will get from Vij, either we will get either X1 or X2, because here we are updating along with dimension J is equals to 2. That means we are updating X2. We are updating the solution 1. पहले solution में 2 चीजें हैं, X1 and X2, and we are not updating X1. We are just updating X2. But after updation, if X2 is beyond this particular range, that is -5 to 5, so what you will do? For that, there we are having the lower bound and upper bound. Always we will have the lower bound and upper bound. So lower bound is -5 here, like I have shown one example, and upper bound is -5. So what you can do is, suppose if it is beyond lower bound, means it is less than the lower bound. Suppose -6 is there. So what we can do is, we can find out the minimum of -6 and -5. So we have to set -5. We have to set the updated solution as -5 along jth dimension, that is second dimension. So X2 will be -5, not -6. Yes, the updated solution is -6. It is giving -6, but -6 is not coming in the range, the constraint. So that is why we have to utilize some other equation in order to limit it. So that is why what we can take is minimum of the updated solution or the lower bound. Similarly, if it is beyond the upper bound, so we have to take the maximum of the upper bound, minimum of the upper bound and the updated solution. Suppose it is giving 10, so 10 is beyond 5, na? So we have to take minimum of 5 or 10. So in this way we can set we can keep in this particular range, and only one dimension is to be updated in the solution in the search equation. Okay, once at one time you have to update only one dimension for a particular, I mean, see, we are updating a particular solution, but solution not complete solution is updated. Yes, definitely we will get the different fitness function because we are updating one dimension. If you are updating one dimension, the value of either x1 or x2 will be changed. So according to x1, x2, you will get different value of fx. So only one dimension is to be updated while updating the solution. Next, the food source of which the nectar is abandoned. The food source of which the nectar is abandoned by the bees is replaced with a new food source by the scout. What I'm saying is that while we are updating the solution, right? While we are updating the solution, so we will get the updated solution. We have to evaluate its fitness. We have to evaluate its fitness. If fitness is better than the previous one, I mean feasible than the previous one, so we have to discard the old one and we can keep the new one. Okay, if it is not feasible with the previous one, what we can do is we have to increase the cycle that we have already discussed, MCN. C is equals to 1 to MCN. When we have to increase the C, initially C is equals to 0. Initially C is equals to 0. If solution is not improving, if solution is not improving for a particular solution, for a particular B, because we are having 5 B in the employed B, and here I'm just talking about the first B is representing the first solution. If the solution, whatever the updated solution we got, which has not improved that we wanted, so we have to increase its cycle number. So C will become 0 plus 1. Initially it is 0. For all 5 B's, the C will be 0. And first we are updating the solution for first B. So if the solution is not improving, if it is improving, C will be 0. It remains 0. But if solution is not improving, we can increase the counter, increase the cycle number. So C will becomes 1. C will becomes 1. And suppose it has reached the MCN, the maximum limit. If any B has reached the maximum cycle number, that is MCN, then that particular solution will be discarded, that is abandoned by the scout B, and the random solution will be kept in place of that, which is written here. Yes, which is written here. The food source of which the nectar is abandoned by the bees is replaced with a new food source by the scout. This is the responsibility of the scout to generate the new solution in place of that. So in ABC, providing, yes, anybody is having any doubt? Okay. In ABC, providing that a position cannot be improved further through a predetermined number of cycles, which is called limit, that is the cycle number, then that food source is assumed to be abandoned, and that particular food is replaced by this particular solution. The random solution we can take, like we have taken in the initial population. Okay. Now these are the ABC control parameters. Like in CSA also we are having many control parameters, like I mean the awareness probability, flight length and all. Similarly in ABC also we are having the swarm size, that is the population size. And if we are taking suppose 10 bees, so 5 bees will act as an employed bee, that is with respect to employed bee we are having the solution in the population. Right, and 50% of the bee, that is 5 bee, will act as an onlooker, which will stay at the hive. And out of these 10 bees, or any one bee can act as a scout bee in order to generate the solution, that is new food source, you can say. And limit is nothing but in order to abandon the particular food source or particular solution. Particular solution represents the food source in ABC, right? We are having the 5 employed bee that are representing the 5 solution, 5 food sources, you can say. Or you can say that in the onlooker bees may exploit a particular food source. 2 or more onlooker bees can exploit a particular food source, but in case of employed bee, it is representing different food sources. So similarly, we are having the here limit. Limit is the cycle number that we have already discussed in the previous slide, and dimension is the problem dimension. Like I will show in the next slide. Here we are having 2 dimensions, x1 and x2. For this particular function, we are having 2 dimensions. So 2 variables are associated with this particular function. So this is the optimization problem, that is the minimization problem. We wanted to minimize the fx, which is expressed as x1 square plus x2 square, and always whatever the value that you will put, that should be in between -5 to 5. Okay, if it is beyond this particular bound, so you have to again take that particular equation, that minimum of lower bound and the value it is giving, minimum of lower upper bound and the value that it is giving, that you have to apply, right? So you have to check the bound, otherwise it is very difficult to satisfy the condition. So always we have to see the bound. Now the control parameters, how to set the control parameters for the given problem. So here colony size is 6, means 6 bees they are taking. Out of this 6 bees, 3 bees will act as a 3 bees will act as a employed bee and 3 bees will act as a onlooker bee. And out of this 6 bee, any one bee can act as a scout bee if we wanted to discard a particular solution, if it is the solution is not improving. So limit for scout, the maximum limit can be 6. So how to calculate the maximum limit for any bee is CS. CS is nothing but the colony size, that is the number of bees, and in this 6 number of bees, 3 will act as a employed bee and 3 will act as a onlooker bee. So 6 into 2, because here we are having 2 dimensions, x1 and x2, 2 variables are associated with the function, means 2 dimensions are there. So that is why 6 into 2 divided by 2. This is the formula for calculating the maximum limit. So 6 into 2, that is 12, by 2 is nothing but the 6. So maximum cycle, maximum times, if 6 times a particular solution is not improving, we can discard that particular solution and we can generate the random solution for that particular position. Okay, and the dimension of the problem is clearly 2 as per the given problem. Now see how you can solve this particular problem. How? Because we wanted to minimize it, na? So how you can solve it? In order to solve this particular problem, so first we have to initialize the position of 3 food sources, which is represented by the employed bees, right? 3 food sources means 3 bees. Okay, 3 bees. So here we have randomly initialized. This is the first food source, because 2 dimensions are there, na? X is nothing but x1, x2. So x1 is first food source is nothing but 1.4112. It is in the range of -5 to 5. That is okay, because both x1 and x2 should lies between -5 to 5. So we have randomly generated it. Okay, these are the random generation. For that, in the implementation part, we have used the random function in order to generate the number between -5 to 5. So the first solution is represented by x1 is equals to 1.4112 and x2 is equals to -2.5644. This is in the range of -5 to 5. Always you have to check the bound. Okay, and the second solution is represented by the second employed bee, which is nothing but 0.4756 and 1.4338. And third solution is represented by x1 is equals to -0.182 and x2 as -1.0323. This is the initial population, and I have already told you 6 bees are there. These 3 bees represents the 3 food sources. These are the employed bee. Okay, and what we have to do is, after that, after the initialization, what we have to do is we have to calculate the function values. So we have to keep in place of x1 square, we have to calculate plus x2 square is equal. If we calculate x1 square, that is 1.4112 square plus -2.5644 square, so it will give the fx. It will give the fx, and that fx is nothing but with respect to this solution, that is first solution, it is giving 8.5678. Okay, and with respect to the second solution, second employed bee, it is giving 2.2820. With respect to the third solution, that is third employed bee, it is giving 1.0990. Initially we have calculated its function value. I mean, function value is calculated. Now we have to calculate its fitness value, right? This is the we have evaluated the function. Here we have evaluated the function. We have to minimize it. Okay, we have to minimize it. But fitness function is represented by this particular equation. That is not fitness one. This one is fitness one. Okay, this one is fitness one, and here fitness function, because we have converted into the minimization problem, function is to be minimized. So fitness function is in the ABC. The fitness function is represented by fit I. I is the index for representing the employed bees. I is equals to 1, 2, 3. If I is equals to 1, that is first employed bee, which represents the first food sources. If I is equals to 2, the second employed bee, which represents the second food source, and so on. So if you want to calculate the fitness with respect to the solution 1, that is this solution or this one, so you have to utilize this particular formula, that is 1/1 plus fi. If you find out 1/1 plus fi, because we have taken the reverse of it, the fitness, that means lesser value will be feasible. Oh, sorry, higher value will be feasible here, right? So 1/fi, if fi is greater than or equal to 0. If you are getting the fitness is greater than or equal to 0, if you are getting fitness is greater than or equal to 0, you have to utilize 1/1 plus fi. Otherwise, if you are getting fitness less than 0, that is negative value. So first we have to calculate the absolute value of the fitness, and then you have to find out the summation 1 plus absolute of fi. With the help of this equation you can calculate the fitness value. So initial fitness vector is, so we can calculate the fitness vector here. This is fi. Okay, this is fi. Remember that this is f1, this is f2, this is f3. This is f1, this is f2, this is f3, or you can say f1x, f2x, f3x. So here this is 1 upon 1 plus function value, right? So what we can do is 1 upon 1 plus 8.5678. So it is actually fi is greater than 0 in all these three cases. In all these three cases, fi is greater than 0. That means you can apply this particular formula, the first one, in order to calculate the fitness with respect to all the solution. So 1 upon 1 plus fi, if you do, you will get 0.1045. With respect to the second function value, you will get 0.3047, and with respect to the 1.0990, you will get 0.4764. Okay, now here this is the minimization problem, and we have evaluated the function value, or you can see here we are taking 1 upon 1 plus fi in the fitness. That means higher fitness value is the feasible solution. Higher fitness value is feasible solution. Don't confuse that when the fitness the value of the fitness will be high, when the value of the fitness will be low, because this is the minimization problem. It is giving the minimum value. Which one is the suitable one? Because 1.0990 is the suitable one, right? Out of these three values, which is most suitable? Because we wanted to minimize it, third one is most suitable. But here the fitness is represented in the form of inverse of the function value. 1 upon 1 plus fi is taken, na? So that means higher fitness value is the feasible one, right? So don't confuse when the minimum, we have to see the minimum value, when we have to see the maximum value of the fitness. Okay, so the maximum fitness value is 0.4764 out of these three B's, or three food sources, the quality of the base food source. So this is the best food source so far. Okay, now the cycle 1. Cycle 1 or cycle 0, you can say, that is the iteration. Don't confuse with the iteration 1 and the cycle 1. Okay, if people are confused, we are at iteration 1 actually. You can replace cycle 1 is equal to the iteration 1. Both are not same. Actually, the counter I am talking about, whatever the cycle that we have taken here for abandoning the food source, and iteration is another thing. Cycle is another thing, iteration is another thing. This should be iteration here, wrongly written here. It is not cycle is equals to 1, it is iteration is equals to 1. Okay, iteration is equals to 1. Cycle is used to abandon the food source if the particular solution is not improving. It is 6 times. If the solution is not improving, we can abandon it and we can discard that particular solution, and in place of that we can keep the random solution by using that particular equation that we have discussed in the earlier slide. Okay, so now we are coming into the employed B phase. After calculating the initial population, its functional value and its fitness, now we are into the, because there are 3 phases. Now there are 3 phases in ABC algorithm. One is called employed B phase. So till now we are at the initialization phase. Till now here we are at the initialization phase. Now we are going into the employed B phase. So in employed B phase, what we can do is, there are 3 employed B. There are 3 employed B. So in order to update the solution with respect to each and every employed B, that is representing the 3 food sources, we need to utilize that particular search equation. So Vij is equals to Xij plus phi ij, Xij minus Xkj. And here I have told you that phi j is the random number which is chosen in between -1 to 1. Xi is the old solution. Xi is the old solution. Xkj is the solution other than Xi. If we are taking the first employed B, so we can update the first employed B with respect to either second employed B or third employed B, because only 3 employed B we are having. If we are having suppose 10 employee B, so the first employee B can be updated with respect to any of the employee B from employee B2 to 10. So that is represented by K. And what do you mean by J is representing the dimension. We can update either X1 or we can update X2. If we are taking J is equals to 1, that means we are going to update X1. If we are taking J is equals to 2, that means we are going to update X2. Whatever, if we are updating X1 or we are updating X2, the solution will be updated. The solution will be updated. But remember that I should not means k should different from I does not is equal, I should not is equals, I is equals to k. You cannot keep I is equals to k. I should be different from k. Okay, so here we are taking k is equals to 1, that is a random number. Actually they are representing 0, 1, 2. We are having three solutions. So I is equals to 0, I is equals to 1, and I is equals to 2. Similarly j is equals to 0, j is equals to 1. J is equals to 0 matlab first dimension, j is equals to 1 matlab second dimension. Similarly k is equals to 0 or I is equals to 0 means first solution, k is equals to 1 means second solution, k is equals to 2 means the third solution, right? So 0, 1, 2. So here we have taken k is equals to 1. That means we are going to update the first solution with respect to the second solution and first dimension. Meaning is that k is equals to 1 means we are updating with respect to the second solution. J is equals to 0 means we are updating the first dimension of the first solution. That is the meaning. So now phi is in between -1 to 1, right? So first what we have taken is phi is equals to 0.8050. That is randomly generated based on the random generator in between -1 to 1. And now you can see what we are going to update the first dimension. So you just see it here. What is the first solution? 1.4112. That is the value of x1, and -2.5644, that is the value of x2. And you can see here we have taken j is equals to 0 means we are going to update only the first dimension, not the second dimension. That is why here v0, the updated solution, x2 is same. We have just updated x1. We have just updated x1 with the help of this equation. So here v1 v0 0 is equals to x0 0 plus the random number, then x0 0, that is the old solution, minus x1 0. So you can take, what is x1 0 here? X1 0, 0.4756. So how we got this particular value, 2.164? I will tell you how we got this value, 2.164. So you can see here is v0 0 is equals to x0 0. So initially x0 0 is this one, 1.4112. Okay, so you have to keep that particular value, 1.4112 here, plus the random number is 0.8050 here. You can take 0.8050. Then again the same value, 1.411, whatever it is. Then minus xkj, that means x10. What is x10? This one, 0.4756. Okay, so we will get the updated v00. So that is 2.1644, and this is same as the previous one because it is not going to be updated. We are going to update only the first dimension, that is the v0. Is there any doubt till now? Because we are updating the first solution. We are at iteration 1 and we are updating the first solution. Similarly, we have to update the second solution. Then we have to update the third solution. Then we will move towards the onlooker B phase. This is the employed B phase. Okay. So what we will do is, yes. So v0, we got v0, that is the updated solution. So first we have to evaluate the function. So with the help of x1 is equal to 2.1644 and x2 is equal to minus 2.5644, we have evaluated the function, that is x1 square plus x2 square. It is giving 11.2610, and the fitness value with respect to this function, 1 upon 1 plus f, because it is greater than 0. F is greater than 0, so we have to take 1 upon 1 plus f. So 1 upon 1 plus 11.2610 is nothing but 0.0186. This is the fitness value. Now we have to compare this fitness value with the previous one. Previous one is 0.1045. Now we are getting 0.08. So which one is greater? Which one is greater? The previous one is greater. 0.01045. The solution 0 could not be improved. Means whatever the solution we have updated, it is not giving the good result. The updated solution is not giving the result. Previous solution is giving the good result because the fitness of the previous solution, old solution, is greater. So that is why what we will increase its counter. We have to increase its trial counter. Means now c is equals to 1. This is iteration number 1, but the counter for each and every b we are increasing from 0 to 1. When it reaches to 6, this particular solution will be discarded. So here we are applying the greedy selection between x0 and v0. So after applying x0 and v0, it is not updating the solution, so we are just ignoring it. Okay. Now, second employed B. First employed B, we have done the updated the solution for first employed B. Now we are for the second employed B. Now with this formula, now we are taking K is equals to 2. Means we are going to update the second solution with respect to the third solution, because K represents 0, 1, 2, right? And J is equals to 1. Now we are going to update along J 1th dimension, means second dimension. Now we have calculated the value of phi is 0.0762. So with respect to this, we have updated the second solution, and which is 0.4756, 1.6217. 0.4756 we are not updating because we are updating along J dimension. J is equal to 1 dimension, that is second dimension. So we have taken the same as previous one. If you see the second solution here, so it is 0.4756. The same we are taking here, 0.4756. We are updating only this one. Right now we have calculated, we have evaluated the function x1 square plus x2 square based on this. So it is giving 2.85, and the fitness value we have calculated because this is the positive value. So we have to use 1 upon 1 plus fi. So if you are doing 1 upon 1 plus 2.8560, it is giving 0.2593. And when we apply the greedy selection between x1 and v1, like 0.2593 and 0.3047. Earlier it was 0.3047. Okay, so again it is not improving. If it is not improving, again we are increasing its trial counter, means for employed B. So for second employed B also, the cycle becomes from 0 to 1. Third employed B, the same thing. Here we are updating the third solution based on the first solution along with the first dimension. Phi we have taken minus 0.06, V2 we have calculated because we are updating 0, so we have taken minus 1.0323, same. You can see here minus 1.0323, same. This solution will, this particular x1 will be updated with the help of that particular equation. Right, and based on this we have evaluated the function, we have calculated the fitness. So fitness is 0.4828. if we are comparing x2, the fitness of x2 and v2, so here 0.4828 is the more feasible one, so that is why the solution is improved. So we don't increase its trial counter because the solution is improved. This is giving the better solution. So what we will do is replace the solution x2 with v2. But earlier in two cases, first and second, we have not updated the solution because it is not giving the good solution. So employed b1 and employed b2 is not updated, but employed b3 is updated because it is giving the good solution. Now after updating the third solution, it is giving the population becomes 1.4112 minus 2.564 because it is not updated. It is not updated, but it is updated. So only difference is that in place of this we are getting minus 0.0754, and with the help of this you can calculate the evaluate the function, this one, then the fitness value, this one. Okay, after that what you have to do, now the employed B phase is over, iteration 1 is over for employed B phase. Now we have to move towards the onlooker B phase, isn't it? Is there any doubt till now? I think there is no doubt. So now we are going into the next phase, that is onlooker B phase. So what onlooker B phase does is, onlooker B phase calculate the probability for each and every solution. So you can see that in the previous phase, these are the solution, and with respect to this solution, these are the function evaluation, means the value of the function, and with respect to the value of the function, these are the fitness. Based on this only we are having the three solution we are having only three, food source we are having only three, but we are having 3 B's and 3 onlooker B's. Now onlooker B operates on these three solutions only, remember that these three solutions only, whatever we are having in the employed B phase. So what it does is, first it calculates the probability. Based on the probability, the information they receive, the proportional to the probability, it updates search the food, or it collects the food, it go to that particular food source in order to collect the food, right? So for if it calculates the probability, what it does is, first you have to calculate the probability based on the fitness value. Fitness value is nothing but this one, 0.0105. So we have to calculate the probability for the first fitness. So 0.1045 divided by 0.1045 plus 0.3047 plus 0.4828. Okay, so it is nothing but 0.1172. Similarly, P2 is nothing but 0.3047 divided by summation of all this fitness. So it is giving 0.3416. Similarly, the probability for third solution is 0.5412. So we have calculated the probability, and based on the probability, it updates the solution. This is the onlooker B phase. It updates the solution. Now coming into the onlooker B phase. So now coming to, again, we are having the three onlooker B's. For the first onlooker B, the same search equation will be used that we have discussed. This equation, the same search equation, the same things has been applied, but based on the probability only. So see here, what we are doing is, first onlooker B, we have taken I is equals to 2. I is equals to 2. We need to update based on the third solution. The first solution, food source is to be updated based on the third solution. Okay, based on the third solution, and here it is not written based on the which dimension. So you can see this one. V2. So based on this, I mean, the fitness is calculated and fitness value is calculated. Now you have to apply the greedy selection between the X2 and V2. If you see the X2 and V2, the solution is not improving. So again, you have to set its trial counter. You have to increase its trial counter. Similarly, second onlooker B, now you are going to update the second food source, right? Then I is equals to 1 is taken and calculated. We have updated, we have found out the V1 value. Then we are calculating the fitness, and if we compare the fitness, it has been improved. So again, we have to set its trial counter as it is, and we have to replace the solution X1 with B1. So after doing this, we are getting this particular solution. Okay. Now when the scout B comes into the picture, when the trial counter, we are maintaining the trial counters for all the solution, I mean all these three solution. If the trial counter for any solution reaches to the maximum cycle number, because we are increasing to the 6 or any value that you have set already, it is not necessary that you have to always fix the 6 colony size into D divided by 2. You can fix 2, you can fix 3, but maximum you can fix is 6. So suppose 2 times a particular solution has not been improved. So what the scout B does is, scout B uses that particular equation, this particular equation, in order to generate the new random solution, this one. In this way, now the iteration 1 is finished. Whatever I have discussed up to this, this is the onlooker B phase. Now the scout B phase. Trial counter we have to maintain for each and every solution. So trial counter is 100. So there is no abandoned solution since L is equals to 6. If suppose L is equals to 2 is taken, and suppose the first solution becomes 2, so you have to discard it and you can update it. So if there is an abandoned solution, the solution of which the trial counter value is higher than L is equals to 6, generate a new solution randomly to replace with the abandoned one, and cycle becomes cycle plus 1. This cycle is, they are talking about the iteration number. So now the iteration 1 is finished. Now we have to move to the iteration number. This is the limit actually, right? So the memorize the best one. After iteration 1, remember that you have to memorize the best one. Now the iteration 1 is completed up to this employed B phase, the onlooker B phase, then the scout B phase. After all the phase has been completed in iteration 1, you have to memorize the best solution, which is giving the fittest value. Now we have to go to the next solution, because now the solution has been updated. You have to utilize this solution. You have to this solution, but out of these three solutions, you have to memorize the best one. Now again, you have to go to the iteration number 2, and you have to follow the same process, that is employed B phase, onlooker B phase, and scout B phase. And you can set the maximum iteration 100, 150, 200, 250, and after all the iteration, whatever the solutions you are getting here you have to memorize the best one from the last iteration. Okay, is there any doubt? Because ABC has been completed mathematical wise, how we can calculate it, and these are the some references that I have gone through. Based on that, I have designed my slides. Okay, so is there any doubt in understanding the concept behind neural network? In the neural network, where we have to apply the optimization algorithm, what the things that need to be optimized, and what is the optimization algorithm, how optimization algorithm works? Is there any doubt up to this? You can ask. Okay, if you don't have doubt, what I wanted to explain is the code that I have shown in the previous lecture, because I think there is no so much time so that I can update I mean I can implement that particular thing, but that is Python code. I want to explain it how it works. Yes, here. So what I have done is, here I have taken the some function that needs to be optimized. So this is the minimization function, and the constraints are given g1, g2, g3, g4. These constraints should be satisfied while minimizing the given function. So how we have implemented it? Now I am just explaining the cross search algorithm. Okay, implementation for cross search algorithm. So here what we have done is, there is the initialization phase. Init is nothing but the initialization phase. So here we are having the n is the population size, PD is the problem dimension, L1 is the lower bound 1, U1 is the upper bound 1, L2 is the lower bound 2, U2 is the upper bound 2. Here we have taken two types of lower bound 1 and lower bound 2. And remember that in the given problem, 4 dimensions are there: x1, x2, x3, x4. You can see here 4 dimensions are there. Okay, so that is why here we are having, in the initialization phase, we have to give how many parameters: the population size, the dimension, the problem dimension. Then we are having the lower bound 1, upper bound 1, lower bound 2, upper bound 2. Then we have taken x. There is the x variable. We are just generating one matrix based on the, I mean, see, the number of samples and the number of features, that is problem dimension, right? So we are just creating the matrix, empty matrix, and one more matrix we are creating here, in which we are putting 0 in place of all the places, cells of that particular matrix. We are putting 0 value. Now we are taking one variable I is equals to 0, and we are just taking one by one each and every crew in the range of n. Means all the random solution is generated in the initial population. So for all the places based on the population size, suppose we are having 5 crores, so all the solution with respect to all the 5 crores, the solution is randomly generated in the initialization phase. So what we are doing is, for generating generating 3 solution, sorry, 0, 1 and 2, I think 4 solution is there now. So 1, 3 in a range of 0 and 1. Whenever you are writing for j in range 0 to 2, so in Python it will support j is equals to 0 and 1 less than 2. Okay, similarly here it is written j in range of 2 to 4, that means 2 and 3. Okay, this particular loop will run for 2 and 3. So we are generating the solution along with the dimension 0 and 1 with respect to the lower bound 1 and upper bound 1, and we are generating the solution with respect to third dimension and fourth dimension based on the lower bound 2 and upper bound 2. You can use any only one lower bound and upper bound. No need to use two types of lower bound and upper bound, because there is a need in the problem, in the pressure vessel design problem. Based on this problem, two types of upper bounds had been set. So 2 dimension has been updated based on the lower bound 1 and upper bound 1, and 2 dimension has been generated based on the lower bound 2 and upper bound 2. But not always for all the cases we have to generate the solutions. Means we have to separately, we have to take 2 types of lower bound and upper bound. Okay, there is the need for this particular problem only. That is why we are having 2 types of lower bound and upper bound. Now, as you know that this particular condition should be satisfied, so we have to write this condition in the code. So how to write this condition? So we have written g1 is equal to, the same thing has been written, minus x1 0, then 0.013 into xi2. You can see here, because x1 is the first dimension, x3 is the third dimension, but how to first dimension minus xi0 plus xi2. This is the third dimension, because 0 represents first dimension, 2 represent 1 represents second dimension, 2 represents third dimension. So similarly here all the condition has been written here, condition, and then conditions is equals to g1 should be less than or equal to 0. You can see that this should be less than or equal to 0. It is written na. So g1 should be less than or equal to 0, g2 should be less than or equal to 0, g3 should be less than or equal to 0, and g4 should be less than or equal to 0. So you have to always write this such type of condition: less than or equal to 0, greater than 0, or greater than or equal to 0. Whatever the conditions are there, if it is not in a proper form, you have to convert it. Okay, so that has been written. Condition, it is written that in condition is equals to g1 should be less than or equal to 0, g2 should be less than or equal to 0, g3 should be less than or equal to 0, g4 should be less than or equal to 0. If all conditions, meaning is that if all these conditions are true, then only we have to generate the population, otherwise not. We have to take only those values of x1, x2, x3, x4 which satisfies this condition, that is g1, g2, g3, g4. Okay, now what we are doing is we are just storing this temporary solution that we are randomly generating into x, and we are returning x. Now the initialization phase is over, means we have initialized the population. So this is all about whatever the function in it we are having, this is responsible to generate the initial population. Now we are next definition means next function, that is the fitness function. Next function we are having random array function. So fitness function, in order to calculate the fitness of function that we are having, that is this particular function, with respect to each and every solution, we have to evaluate this function, right? That is the fitness here. That is the fitness here. So that is why this function is responsible to calculate the fitness. So what is written here is, for this we need to give the particular xn. I will tell you what do you mean by xn here, and the number of samples and the PD. Okay, that is the dimension. So as you know that n and PD always is to be given, because n represents the number of sample or number of crows, and PD is the dimension, and xn is the solution. Xn represents the current solution. Okay, so now we are taking the one variable fitness where we can keep the fitness values. Now we are just running this particular loop for each and every cruise, and we are appending fitness dot append. All the fitness value is appended to this particular variable with respect to all the cruise. So first it will be appended. If we are calculating it, we can append the fitness to the fitness variable. Then if you are evaluating the second function, I mean the solution, we have to append again the fitness value to this particular array. So fitness is the array which keeps all the fitness value with respect to all cruise. Now we can return all the fitness value with the help of return fitness. And similarly here random number is generated in between the range. So in between the range we need to generate it, because always generation, I mean the range is there for each and everything. So in order to generate the random number, we have taken the, I mean see, what is the purpose of this random array? Because we are discussing the crow search algorithm. In the crow search algorithm, as you say that we have to select two crows, which crow is following to which crow. So which crow is following to which crow? So for that random array we are having. So suppose there are 10 crows. So crow 1 is following crow 2, maybe crow 2 follow crow 10. So for that we are generating the random array here. To which crow means every crow has hide their food. So one crow wants to take the food of crow 3. So crow 1 is following crow 3. So in order to keep that one, here we are generating the random array in order to maintain which crow is following to which crow. That is why here it is written rd append in int, because it is generating random number in between any random number. Random number may be 0.1. That is why here we have taken math.sil function in order to have that particular thing. So random array function is used to generate the random array for the crows in order to following the other crows in order to get the food the particular crow has hidden. Okay, now here the control parameters. PD is nothing but the problem dimension. For this current problem, dimension is 4. N is equals to P. We have taken the 50 crows, and here AP awareness probability initially we have taken 0.1. Flight length we have taken 2. Lower bound 1 we have taken 0. Upper bound we have taken 100. It is as per lower bound and upper bound is as per the given problem. For this problem that we have chosen pressure design problem, based on this the lower bound and upper bound has been set. So lower bound 1 is equals to 0, upper bound 1 is 100, lower bound 2 is 10, upper bound 2 is 200, and count is 0. That is iteration number. Count is nothing but the iteration number. Now x is equals to numpy dot matrix, that is the init. We are calling the init function, this function, in order to initialize the population. So here what we have passed, and the number of crows, their dimension, lower bound 1, upper bound 1, lower bound 2, upper bound 2. Now it is performing initializing all the crows with the help of this particular init function. Okay, then what we are doing is, after doing this one, right, it will return x. You can see here it will return x. Now what we are doing is, again we are taking one more variable, that is x new. You can say x new. So x new, we are just copying the same thing, whatever we are returning this particular initial population, this function we are copying into the xn variable. Then what we are doing is, again we are calling the initialization function in the next iteration, right, initialization. Then we are calculating the fitness for that all the crows numpy dot array, we are calling the fitness function, and we are passing xn nn pd, right? Then we are memorizing mem. You can call it as, we are having two types of matrix. One is the location, another is the memory, that is the food. So we are copying all those into the memory. Then we are calculating the fitness of all those crows based on the ft dot copy. See here, fitness underscore name is equals to ft dot copy, right? Because we have called the fitness value. Then we are keeping all the fitness value into the ffit means array, ffit array, and the t iteration number is maximum is 1000. Then what we are doing is here, in the t, if t in a range of t max, that is the iteration number, we are just calling the random array in order to maintain which crow is following to which crow. Then in x new array, we are taking the empty values. Then what we are doing is, if for as we have maintained, if I in a range of n, there are n crows. So first we are taking the first crow. If the first awareness probability, that is r1, is greater than ap, r1 is greater than ap means awareness probability is low. Awareness probability of crow j is low. So for j in range of pd, for j in range of pd, because problem dimension, we have to run this particular algorithm along with the dimension, we have to calculate x new, we have to calculate x new, right? Based on that particular equation that we have discussed. If the j is unaware of I, if j is unaware of I, so we have used the lower bound minus lower bound minus upper bound into random number. So we can use this one. But as we have used two types of lower bound and upper bound, that is why if j is in range of 0 to 2, so we have to utilize this particular equation. If j is in a range of 2 to 4, means for dimension 2 and 3, we have to apply this one. So that has been coded. Then then for I in a range of n, what we are doing is, here we are satisfying the condition. The condition is always, while updating the solution, always the condition should be made, g1, g2, g3, g4. So that's why we have written here all the condition. So if all the conditions should be true, it is in same equation, right? It is in same for loop. For loop is not ended here. We have kept in the same for loop. If condition is true, so if all condition is true, for j is in range of, so we can update the new value to that particular location. So now here in the ft variable, we are keeping all the fitness values, and then now what we are doing is, we are calculating what we are calculating is here we are updating the position and memory here. After updating in position and memory, we have to compare the fitness value, the old value and the new value. If the new value is greater, then we have to memorize it, otherwise we can discard it, same thing. And all these things are maintained in ffit. Here numpy.min is we are maintaining the best value, and based on this ffit we can find out the best value after all the iterations. So what is written here, print ffit 0, it is wrongly written here. In place of 0 you have to find out -1. -1 is nothing but the last one, that is the best value. If you are writing here 0, so it will give the least value. So here you have to write in the code, it is wrongly written. It should be 0 should be -1, so that you can base 1 after all the iteration. That is why here it is written t in a range of t max. It is the iteration number. So this for loop is this particular program, whatever it is written, it is run for 1000 iteration. When the 1000 iteration reaches, then only it prints ffit -1. If ffit -1, that is the best value. So this is the whole program that I wanted to explain for the crow search algorithm. Similarly, we are having the code for Python also, but I'm not going to explain the code of Python. Instead of, I'm just going to call one of my team members in order to explain the ELM, how ELM can be optimized using the optimization technique. So Jyoti Ranjan, are you there? Just I'm calling him. Just wait. Okay, Jyoti Ranjan, you are there. I got your message. So I'm just going to stop my PPT, and you just share your PPT and just explain how to optimize ELM, because ELM is one of the neural network technique which is widely used for time series data, and stock market is one of the time series data. So how we can optimize, how we can improve the accuracy of ELM by using the optimization. So I'm just going to stop this one. You just share your PPT and directly you can go to the code. No need to explain the PPT, because if you explain the PPT, it will take so much time. So you can directly go to the MATLAB code. You can open the MATLAB browser where you can explain the steps step by step. You just first explain the implementation of ELM. Then in ELM you have to explain which parameter needs to be optimized, needs to be tweaked, and how it has been devised into the objective function, and how the objective function has been optimized in order to improve the accuracy of ELM. That is explained by the Jyotiranjan Nayak, which is one of my team member. I'm just going to stop this presentation. Okay, Jyoti, you can share your screen.
Yes. Sir, is it visible?
Yes, visible, Jyoti. You move ahead.
As sir said, we can implement this two search algorithm to optimize the weight and bias of extreme learning machine, and we can use this for forecasting the stock market price. And as you can see my slide, this is this S&P 500 trend we are using to forecast, and this is the data what we have considered for this study. And we have 1 year data, means 255 numbers of trending days are there in 1 year. For that reason, this is the data but we have given. And then I am going to coding. So this is the MATLAB coding I have here. This is for if, as I said that I have the data in this worksheet, and this is the total data I have considered 254 data, and in sheet 2 I have separated my training data and testing data, and in training data I have taken 181 number of observations, and in sheet 2 I have the testing data. So I am going to call the sheet 2 as I am doing the training process. So I am calling the sheet 2 data, and this is nothing but a total data, training data I have considered as K1. And now as ELM has one activation function like a sigmoidal activation function, and exponential of that activation function means negative higher value will be 0, so it will be give you infinity. For that reason we want to normalize the data. Whatever we have the data, we have to normalize the data in between 0 to 1. For that reason we have written this coding. So to normalize the data is total training data from 0 to 1. And as sir said, these are the variables of two such algorithm. Means awareness probability we are taking as 0.1. This is the generalized awareness probability, and flight length we are taking as 2. And you can take 2 or 1, whatever it is, but it's generalized flight length will be 2. And I have taken this lower boundary of weight and bias as -3 to 3. This is the boundary condition we have to follow. This weight and bias of ELM should be in between -3 to 3. And this is my input and output. Here we have taken 3 inputs and 1 target. Which I show you. This is my open, high, low, and close. So open, high, low data we are taking as the input, and closing price of the stock we are taking as the target. So here we are giving 3 data as input, and last data is the target. So this is the total input data for training period, and this is the total data for testing period. Here I have taken from 2 is to length of this training data. Why? Because we want to predict the next data, means 1 hour ahead data. As our data are time series data, means we have to predict the next day data. So we have to take this input target from 1 to n-1, and target from 2 to n. So training data for training data 1, we have to predict the target of 2, and this is the total number of training data we have considered. And we have to set the number of inputs, means 3 inputs we are taking, like n equal to 3, open, high, low prices, and m is nothing but your hidden neurons, how many hidden neurons you want to take, and I have taken as 10, and it may vary as per the system. And as the CSA has to be run with the maximum iteration, we have maximum iteration is 500, this maximum iteration, and the number of population means number of rows I have taken as 30. It is a user defined. You can change as per your system. And this is the number of population for weight, because we have three inputs, so we have 10 neurons, so our weight should be 3 into 10 should be 30. So for that reason, this is the number of population of our weights. So this is the number of population of rows means 30, and this is the number of inputs we have taken is 3. So it will be a 90 cross 3 matrix. This is your weight. And then we have to initialize our weight and bias. We have to initialize our weight and bias in between lower boundary and upper boundary. It means boundary condition. CW will be lower boundary into random number plus random number into upper limit minus lower limit. This is the process how we initialize the weight, and this is the coding for initialize the bias. And the bias, and this is the here you can see this L11 is the size of W, means size of weight here, and this T1 and T2 we have taken to collect the data, and K1 K2 also same purpose. I will discuss later. And this is how, this is the coding of ELM. This is the coding of ELM. We pass the weight and bias what we have initialized here in this 27 and 28 line. We have passed this weight and bias data in ELM, and this is the H matrix, H calculation of ELM, which we have to calculate the H matrix, and after that H matrix we have to pass it to activation function, and this sigmoidal activation function we have to consider here. We consider in the ELM, and after that H train means activation function, we have to calculate the beta, which is nothing but your weight of output and hidden layer weights. So this is the formula inverse of H train, and this one the formula for beta calculation. And after beta calculation, beta and H train output of sigmoidal function will give you the actual output of the ELM. And after getting this actual output of the ELM, we have to calculate the error. What is the output of ELM? And this is the our predicted or target we have considered. And this error is nothing but our objective function, and this is the error, and this square of this error and mean of the square of this error is nothing but MSE, mean squared error. We have taken this as an objective function of true search algorithm to minimize. So this is the objective function of our true search algorithm. So this is the mean square error we have to minimize, and accordingly here K1 and K2 value will be updated, because here W will be from 1:3. As we have n is equal to 3 here, then 1:3. First we have to consider 1:3 W. Then after one iteration, it will be changed to 4:6. 4:6. Accordingly, we have to update the weight here so that we can change the H1 and H value. And for each number of population, we have objective functions. This size of this objective function is nothing but the size of the number of population. And now we have this objective function. Now this objective function, we have to calculate the minimum of this objective function. We want to minimize the objective function, so we have to calculate the minimization of this objective function, and this minimum value will be stored at the AA1, and indexing of this minimum of this objective function will be BB1. Means this population, means if BB1 will be 5, then fifth crew is the best crew among all the crews. And WM is nothing but your memory. In first iteration, we have to pass the initial crews as our memory of the crews, and this is the memory of our biases. And this objective function of memory is nothing but your objective function we have calculated, because this is the first iteration. We have not entered into the iteration process, and then we have to enter into the iteration process. So here we have taken IT as current iteration. From 1:to iteration max we have considered as 500, and then as I said, this number means we have to update the crew by using a randomly selected group from the number of population. Means if you want to update the first group, then we have to choose a group from the number of population rather than first group. Except first group, we have to choose one group from the population, and this is the way how we got the random groups from the population. And again here, if the same techniques we have used to update the weight and bias. This is the updation of weight and bias, as sir said. We have to update the weight and biases here. This is the updation of weight by using flow search algorithm. If random value is greater than AP, means this is the awareness probability. If random value is greater than the awareness probability, means phase 1 of the flow search algorithm, then this is the equation for updation of W, means weight. So this is the old weight we have initialized before, and this is flight length, and we have to multiply one random value, and then this is the memory of the crew. Memory of the crew means randomly selected crew. Randomly selected memory of the crew. This is the randomly selection crew, and then minus this is your old weights. And similarly, we have to update the B value. This is the phase 1 completion of weight and bias. If that random value less than awareness probability, then what will happen? We have to replace this weight and bias value by randomly. This is the random replacement of the weight and bias if that random value greater than awareness probability. So this is the process of operation of weight and bias. This is and as we have taken K1 and K2 have two values, 1 and 3, then it will be W will be updated from 1 to 3. Then next iteration it will be next for loop I equal to 2, then it will be 4 and 6. Accordingly, our weight will be updated. This is for only weight updation. Then now we have to check whether our weight and bias, whether our new weight and bias which are updated is inside the boundary or not. We have to check the boundary condition. So here we have this is the condition. Here GH is the size of W new. Means whatever we have updated the W, we have to find the size, and this is the number of rows of this W, and this is the number of column of the W. And accordingly, we have to check whether our W new means new weight is less than lower boundary or not. If it is less than lower boundary, then it means it violates the boundary condition, so that we can assign that W new. We can change that W new as the equal to lower boundary. And similarly, if the new W is greater than upper boundary, means it is violating the boundary condition. For that reason also, we have to set this W new, particular W value is equal to upper boundary. Similarly, for bias, we have taken another condition here. So this is the here we have size of bias GH1, and the row value will be the I value will be the assigned to row value, and J will be varies from 1 is to columns value. And similarly, we have to check whether it is lower than lower boundary or upper higher than the upper boundary. It means violating the boundary condition or not. If it is violating, means we have to set it at lower boundary or upper boundary values. So this is the condition in which we can set the values of weight and bias inside the boundary condition. Similarly, here we got the new weight and new biases inside the boundary value, and then we have to check whether these new values, we have to evaluate the functional value, means objective function we have to recalculate with the new weight and biases. For that, similar process what I have used in before the iteration, we same thing we have used in here also. Here also H matrix we have to update by using new weight and new biases, and here also we have to pass the weight S2 value in sigmoidal activation function, and then we have to change the beta value in terms of H trend, newly calculated H trend and our targeted value, and then we got our new trending or new target value, new output of the ELM. Then again we have to calculate the error using that newly calculated trend value, and minus this is the target, actual target of ours. So the square of this error and mean of the square of this error is nothing but your objective function. This is mean square error. This is the new objective function. Objective 1 is nothing but your new objective function after one iteration. Similarly, this is for weight and weight calculation, k1 is to 3 and then 4 is to 6. For this we have taken as k1 k2. Then this is the objective function. Objective 1 is a new objective function. We have to calculate which objective function is the best objective function among all the crows. So this is the put A2 is nothing but your minimum objective function obtained by the crows, and BB2 is nothing but your index, means which crow is giving you better result, means which number of population is having high means better and we have to find that BB2. And then as we got the minimum value, and we have to calculate here in this section, we have to check whether our objective function what we have got after the new objective function, and we have the objective m, which is nothing but for first iteration, this is the memory objective function of the memory. So this is nothing but your old objective function, and for first iteration, if this new objective function is less than this your memory objective function of this memory, that means the new objective function, new fitness value is better than the old fitness value or the memory of the close fitness value. For that reason, what we have to do, the memory of the weight, means weight memory, we have to change by new memory, new weights, because new weights having better fitness value than the memory weightness value. Similarly, we have to change this BM also, because this is also BM new is having better fitness value than the memory value. And similarly, we have to change the objective function or objective function of the memory of the group. Now this is the total updation of our weight and bias and objective functions after each iteration. For each iteration, it will check whether our new objective function is better or not. If the new objective function is better, then a new objective function, new weights and biases will be considered for further iterations. Otherwise, the old one is the better, then we can consider the old weights and biases. Now, again, the old W and old B, means old weight and old biases, will be updated by the new ones, because we have here updated memory WM and BM. We don't want to update the W or old weight and old biases according to memory. We have to update the weight and biases according to the new weight and biases or new cruise positions. And then again, we have to find the best value in each iteration. Each iteration we have to find which one the best, means minimum objective function of n, means memory objective function we have already updated, whether it is a new objective function or old objective function, that is objective function of memory. Then we have to find the minimum objective function, that is nothing but your AA3, and then the position of which is having minimum objective function, that is nothing but your BB3. Now accordingly, which this BB3 is nothing but your weight of the position of the weight or position of the biases of the population, which gives the better fitness value. For that reason, what is the G best weights? This is the G best weights for each iteration. This is the G best weight new, which is nothing but your memory of BB3. BB3 means this index. -2 means here, if this is the value is 10, it should be 10 into 3. Number of inputs is 3. 3 into 10 is 30. 30 minus 2 will be 28. It will be 28 from 28 to 30, means 28, 29, 30. So it will be 3 weights for 3 inputs, and the row column size will be 10, because we have taken the 10 number of neurons. So it will be 3:10. For each iteration, we have best weight values like 3:10 values. And similarly, BG best new means for each iteration we have the best biases. Here, this is nothing but here. This is biases is for each neurons, that will be 1. If you have taken 10 neurons, that will be biases value will be 10 for each iteration. So it will be position of this BB3. BM is the 10 number of BMs, 10 number of biases will be there for each iteration. Similarly, best fitness will be this one. So we have minimum fitness value. This is the minimization problem. So this is the best fitness value we have. This is best. Okay, then if you want to save all the results, means all the weight and biases results of each iteration, then you have to write this. Means from per T1 is to T2, T1 is nothing but your 1, then it will be 3. 1 is to 3. 1 is to 3, you have to save this as WG best, whatever got from this iteration best value. We have to set it to result W, and result B is nothing but your results of biases, best biases of each iteration. Similarly, we have all the results each for each iteration. If we have 500 iterations, then that means after 500 iterations, we have this result W of size of 1500 into 10. 1500 cross 10 with the metric size. 1500 means 500 iteration, each iteration having 3 cross 10 weight size. And similarly, the result of B size will be your 500 cross 10. 500 is the iteration and 10 is the neuron size. Similarly, this is the fitness of each iteration. This is the fitness value. It is written for evaluating the convergence plot, and we have to plot the convergence plot. For that reason, we have written fitness ID. Each iteration we have to calculate the best fitness. This is the case, and this is the end of true search algorithm. After training process completed, we have the best results. Means this is the best results, WG best new and BG best new. After 500 iteration, this will be the best values, and then we have to go for testing of the data. Then we have to, this is the testing method. Again, as I said that in Excel sheet we have taken in sheet 3 we have taken the testing data. Again, we have to call the third sheet. Yeah, this is the format for calling third sheet of the spreadsheet. Then we have to evaluate the size of the data, because we have to calculate the or normalize the data in between 0 to 1, and this is the process how we get the normalization of the data. Then we have to separate the inputs and outputs. We have 3 inputs and we have 1 target. Then we have to take number of inputs as means input we have to take as 1 is to n minus 1, means 1 is to n we have to take. Why? Because this input is nothing but your if 1 is to n is a target. As we predict the next data, means next day prediction is there. For that reason, next day ahead prediction means we have to take the next data, means we have to consider second data if you are taking the first data as input. So we have to take the second data as output or target. So this is how our input and output, input and target is set. And this is the total length of testing data, means how much length is the testing data have. And the same process what we have done in the true search algorithm, we have to find the H value, and here we have written WG based new means what? Means after 500 iteration we have this much of W best value, means weight, updated weight, and this is the updated biases, and we have calculated the H value here, and again we have to pass it through activation function, and again we have to calculate the beta value, and again we have to calculate H test, which is nothing but your prediction value. This is the predicted or output of the ELI. Again we have output of the ELI. We have to convert it to our original data, because this is a normalized data we have operated, and we, for that reason, we converted to or denormalize the data. This is the denormalization process. Denormalize the data to original predicted data. And again, this is the actual data what we have taken from the Excel sheet, and we have calculated the error, predicted data minus actual data, and we have calculated the MSE. Then we can plot this predicted data and actual data here. As we run, this is a number of population we have taken 30, and iteration maximum is 500, so it will take a little bit time. It's 2 to 3 minutes it will take. See, as you can see here, this is the current iteration value is updating, and here this is the means MSE values of each iteration. So it will run, and this is, it will take a little bit time. And as we are saying that this is for 500 iteration max for better use, or actually for we have to run this for 20 runs. 20 runs means we have to run this again and again for 20 times, and for each 20 times we have 20 best results. Among them we have to evaluate which one is the best result, and accordingly we have to extract the data. This is for one run. If you are taking iteration max as 500, then it is completed, then that means this is for one single run. If you run this again and again for 20 times, then it will have 20 best results, and you have to compare which result is the better one. Accordingly we have to evaluate the best prediction values, and as you can see it is up to 500. Okay, this is the prediction value. Okay, it is commented for that reason. So this is the figure 2. We can call the figure 2 here. And we can hold on this, and then we can plot this. So this is the actual data. Red one is the actual data. The red one is the actual data, and the blue one is the predicted data we have. And as I said, we have to run it to 20 times to get better result. So we already have run it for 20 times, and we saved it in Excel sheet. In sheet 4, we have the data here. This is the actual data. A column is the actual data we have, and B column is for the CSA optimized ELM data. But this is for 20 times we run for 500 iteration maximum, and we got the best result here, this one. And this is the result of ELM, actual ELM proposed by Wang et al. So as you can see, this is the ELM model, and this is actually this coding is done by the author Wang et al. And we compare the data. Is we compare the predicted values of actual ELM achieved by the authors, and we have our optimized ELM values. So this is SP500 Excel sheet, and again calling, and my results are in fourth sheet. For that reason, this is the actual data. Means first column will be my actual data, second column will be my data predicted by CS optimized ELM, and this is my third column is nothing but my data predicted by my actual ELM proposed by the authors. For that reason, we run this. See, as you can see here, blue one means data one is nothing but your blue one is nothing but your actual data, and this red one is nothing but your CS optimized ELM, what we have done, and this yellow one is nothing but your actual or original ELM proposed by the authors. And as you can see,
Ranjan, can you magnify it, the graph, so that difference can be easily seen?
Okay, sir, is it visible now?
Yeah, it is visible.
Sir,
actually what here I wanted to draw the attention is that the blue one is the original one, and this one is the blue one is original, right?
Blue one is the actual data.
Right, original one, and data 2 is the optimized ELM by CSA, and the yellow one is the simple, I mean the result from simple ELM. So it is very close, means over the proposed, if we are using the optimization technique into the ELM, so it is giving the better results of better predictions that we wanted to show here. Means whenever we are optimizing the parameters of neural network, that is ELM here we have used. So if we use optimization technique with the neural network, it is giving the better accuracy than the standard or the conventional ELM that we wanted to discuss here. Okay, continue now.
Yes, sir. Yes, sir. Then we can compare the error calculation also. MSE values means here you can see our MSc is 274.44, and for ELM this is 945.21. It's almost a very high margin. We are improving the ELM performance by using optimization technique. So this is how we can optimize this. But the thing is, it will take little bit more time in compared to actual ELM, because we are iteratively we are updating the ELM value and all these things. And as you know, the
When
ELM
we use optimization technique to any conventional technique, always it will take much time, because
much time.
yes, iteration is meta-heuristic techniques is based on the iteration. Many times we have to perform the same computation in order to get the better accuracy. So always it will take the much time than the conventional one. But if you are, I mean, see, if many of the participants are doing the research, if you are taking some other optimization technique other than CSA, maybe ABC or PSO or any other technique like WA or GWO, that is Gray Wolf optimizer. So CSA takes lesser time than those WA and GWO. So it depends on the parameter to be tuned and the calculation it performs. So there is a simpler calculation in CSA than the GOA and the WA. So you will get the, I mean, the time it takes, it is very lesser than those other algorithms. Okay, continue, Ranjan.
So actually here is the number of population, iteration maximum, how many times you want to run. Those things also affect the time consumptions of the CSA optimized ELM. As you know, that only for a single time in each iteration we have to obtain the objective function for once. This is the objective function we have to calculate in each iteration for once. But in other optimization techniques like TL view or symbiotic organism search, those optimization technique you have to calculate the objective function for 2 times. Means you have to call the function for 2 times. So it will be take almost 2 or 2.5 times of time consumption as compared to CSA. So this is the benefit of CSA. And as you know that hidden neuron, we have taken that it is a constant value. It's 10 number of hidden neurons we have considered as 10. You can change this also 10 or 12, 25, whatever it may be. But accordingly, your time consumption will increase because your parameters of design parameters of the problem will also increase. And as you can see here, if you run this, it will be take very less time. If you want to calculate the time consumption, you can write peak in front of before the program run, and after the program you can write top. So it will give you the time consumptions by the ELM. This will be 0.70 4 times 1. And if you will run this at CSA, in CSA, if you will take this, it will take a lot of time. But this is the offline process, means optimization technique it is an offline process. So after getting weight and bias, updated weight and bias, you can install that weight and bias, or you can assign that weight and bias to ELM. So it will behave better than the ELM, which has only randomly chosen weight and bias. Actually, in original ELM, we have the input weights, we have to set it at random. Only the output weights will be updated in original ELM. But here we are optimizing the input weight and biases. Okay, after getting the best value of weight and biases, if we will set that weight and biases to ELM, it will guaranteed give you the better result in comparison with the original ELM. So if you want to use your top, okay, let's use for 100 iterations. That one is for 0.7 second ELM, but here as you can see, it will take a little bit more time. Okay, this will be for 18.1570 seconds. It will take. So this is little bit more time consumption, but if your system requires better accuracy in comparison with ELM, you can
I
choose.
wanted to draw the attention here that as we have applied this optimization technique for the problem of stock market prediction. So here money is very important, right? Yes, it can take 18 great test seconds. The ELM has taken only 1 second, nearly 1 second, and it has taken 18 seconds. So it's better to wait now for 18 seconds. If it is predicting better than the previous one, so why not to wait for 18 seconds? So here the time is not important for this particular application, but for some of the application time is very important. So where if time constraint is there, so always meta heuristic technique takes time. So it depends on problem to problem where we have to apply the meta heuristic technique. If time is not so much important, so you can apply the optimization technique always.
Yes, sir. So actually, this is all about CS optimized ELM. And
so I think Ranjan Naik, we have already discussed the ELM and we have already discussed optimize ELM, right?
Yes, yes, sir.
So the floor is open for the question if you are having any questions, because as per the time constraint, we cannot discuss more advanced techniques. We have discussed only the basic techniques, that is ELM, and we have optimized the ELM by using CSA. And we have already explained the basic concept of CSA. In fact, we can optimize this ELM with ABC also, any meta heuristic technique. So floor is open for the question. Any queries, participants?
We are having one participant. She is having doubt. Jayashree Wagmare. Ma'am, if you are having a question, you can ask directly from the sir.
No, sir. Hello?
Yes, Jayashree ma'am, please continue.
No, sir, no.
Okay.
It was by mistake. No, sir.
Okay, okay. If any participants having any question, they can raise their hand. I will unmute from here, and you can directly ask a question from the sir. Or you can also write your question in the chat box. Okay. Okay, sir.
Okay, sir. I think no question from participants. Participants, you may record my, you can take my number, personal number, that is mobile number is 9826551906, and my email ID tpsahu.it@nitrr.ac.in, right? You can, if you are having any doubt, you can mail me, you can contact me related to the machine learning, the classification algorithm. It may be the single level classification or multi-level classification, how to formulate the problem, where to use optimization technique, if you are working in. So definitely I will try to give the answer. So it's better to mail the query so that I can have that particular question. I can have the time and I can reply to that particular mail if you are having any query. Thank you, sir. Thank you, Pankaj sir, for
thank you, sir.
me.
Sir, kindly share your PPT now.
Definitely, sir. I will mail you. I think the mail in which you have given the invitation, I will mail you the PPT.
Yes, yes. Thank you, sir.
Okay.
Thank you. Thank you.
Okay. Thank you. Thank you, Jyoti Ranjan.
Okay, thank you, Dr. Tirath Prakash Sahu from the NIT Raipur for speaking at 1 week Atal FDP organized by Rungta College of Engineering and Technology, Bhilai. Your presentations on the neural networks and its applications was very knowledgeable and was very well received by our participants. Thank you, sir.
Thank you. Thank you.
Thank you, Ranjan also. Once
Thank
again,
you,
I
sir.
thank you for your enriching our event with your presence. Thank you very much, sir.
Okay, thank you.
Dear participants, within 2 minutes, we'll be starting our next session. The speaker for this last session, session number 3 for the day, Dr. Deepak Kumar Devangan is available with us. So we will start within 2 to 3 minutes. Please wait.